Good, so welcome to the afternoon tutorial for BrainScaleS 1 and 2, and we will start with BrainScaleS 1. And for this, I'm going to quickly walk you over what the BrainScaleS 1 machine is. So what you'll see in the upper picture is the machine room we have at our institute in Heidelberg. And in there are 20 so-called wafer modules. So we're going from the outside to the inside. So now we are in the machine room. And these prominent red cables are the Ethernet connections to the FPGA, which then talk to the neuromorphic heart, which is a wafer, as the name suggests. So what you see here is a wafer module, and there's, as I said, 20 of these. And they have a couple of peripheral printed circuit boards for communication and power supply. And of course, the wafer, the silicon wafer, is at the heart of it. So one of these wafers consists of about 400 chips, and each chip has 512 neurons. So what we do is we leave this wafer intact and put an additional metal layer on top, which connects all these chips, so that you have something like a very large integrated circuit chip. So all chips can talk to each other via these additional communication layer that is on top. So when we now go down to the single chip, you see the different areas indicated. So here on top you have one synapse array, and then on the bottom half you have a second one. These chips are usually in some form or the other symmetric, so here we have a horizontal symmetry. And what you can already see is that the synapses take up much more room on the chip than the neurons do. And this already gives you an idea that for a neural network, the connectivity, the synapses and their weights are crucial. Of course, neurons as well, but the ratio tells you something. So now we've gone through all these different steps of integration. We can go back to the outside, because this is actually where you and I are. Yeah? We are more like located right now, when you open your browser in a minute, on one of these computers here, and you have to talk to the silicon wafer. You have to configure it, and this is done by a large software machinery that we try to hide as best as we could from you, so that you can focus on the task of creating and configuring the neural network. This is neurons, populations of neurons, and connections between them. So let's get you started with setting up your browser. So you should first connect to the Tel guest Wi-Fi. Password is bicycles. And if you've done that, you can navigate to the URL, which is written on top. This is brainscales-r.university-heidelberg.de, and I think we have to add a /demo at the end. Yeah? Yeah. So if you've done that, you will be asked twice to enter username and a password. For the first time, you enter demo user in BrainScales. Be aware that the B and the two S's are capital letters. And after that, you can choose freely a username, for example, first name, last name, and the password is again BrainScales. And if you've done that, you should see a directory listing with two directories, BrainScales 1 and BrainScales 2. You should go to BrainScales 1. This is how it should look like, and then you open that. Then you open the IPython notebook, and there you are. So please let us know if you have accomplished this first task.
Subdomain was missing. KIP. Kirchhoff Institute for Physics. Sorry.
So that AID value?
Yes. Okay. So then
BrainScales -r.
U and I minus .de is /demo. Yes. just choose whatever you like. It generates a home directory for this user.
Okay, so if you've successfully opened it, please scroll down a bit, and then we will together start to execute a bit of code. So the first is to assign you your own FPGA. This is so that we can all work in parallel on the same system. You execute these by pressing Shift and simultaneously press Enter. Then it should get a number. And the second cell here is the script that we are going to execute. There's some boilerplate code in here, but the interesting part starts with the neuron parameters. And they are given in the natural units of neuroscience, which basically means that you set a couple of units to 1, like you usually do in high energy physics. And then all these numbers translate naturally to each other without having to care about the units. So if you know a bit about biological neurons, then you will recognize different potentials, recent potential, resting potential, and they are set here to -30 or -20 millivolts, and then a couple of time constants, membrane time constant, refractory time constant, and the time constants of the synaptic interaction. So what we are then going to do is we are going to create a population of 2 neurons, and we will we need to place it on a specific Heiken chip because the autoplacer would put it somewhere differently, and we need to make sure that we can all work in parallel, yeah, so that we have a set of Heikens that do not overlap. Then we are going to read out the membrane potential of these neurons, and the next lines we are going to uncomment in the following. So first we start really simple, just having 2 neurons, recording the membrane potential, basically doing nothing apart from that. Then we start the experiment and we store the results. So what you see here, and also this is true for the neuron parameters, is that times are given in milliseconds. But if you remember Johannes' talk, or also introduction this morning, we told you that the neuron dynamics on chip develop accelerated. This is just because of the properties of the substrate. So in wall clock time, this 500 needs to be divided by a factor of 10,000. Yeah. So you can think of large experiments that take minutes or hours are getting compressed to a manageable time scale. So we will also execute this cell and the next one, and the next one schedules this experiment on the system. And if the hardware is not occupied, you will see some messages going through telling you what the machinery is doing. For example, configuring the chips, writing the neuron parameters you've requested. And if all went well, you should see at the end a message storing results and done. And then we can execute the next cell, and we take a look at the free membrane. So please follow these instructions and see that you get the plot. Sometimes you have to execute this plotting cell twice for some reason. And then please let me know what you see, and compare with traces you see on the screen.
I've got a bunch of spikes.
You get a bunch of spikes, but only in the upper plot, right? Nothing in the lower one?
No, I have a spike raster in the bottom.
You got a spike raster at the lower one. That's peculiar. If you get a spike raster, then you should try to increase the spiking threshold. So you go to the neuron parameters and you increase the threshold until it doesn't spike anymore. So we want to start with a free membrane. Mm-hmm.
But what we can already see, it looks different because it's analog. And we have some spikes during the readout in the membrane, just the readout noise.
Yeah, so you see some specialties. So if you take a look at your neuron parameters, you see that although we requested the free membrane to be minus 20 millivolts, you get two neurons that are different from that. The one is closer and the other is a bit far away, a bit further away from the requested membrane voltage. And this is something that you will always get to a certain degree. This you could compensate by now shifting these membrane potentials, but basically you always have a distribution. And this is because you have, for every neuron, a dedicated circuit, as for the synapses as well, but here only the neuron circuits matter. And every neuron is different from the other because this is all dedicated circuits. And this is already calibrated, but only to a certain degree. So over time it maybe drifts a bit, and also calibration is not always perfect, so you will get a distribution of membrane potentials close to the desired value, but still with a certain distribution. And you see that different from simulation, you get some noise. This is from the readout chain. There are then basically cables connected to the membrane capacitor, and along the way they pick up noise. So this is most probably not on the membrane itself, but it's just an artifact. If you would record long and average, this would vanish. So on some of these readout lines, you could also see some larger spikes or fluctuations on the membrane. This is when the readout line picks up some noise from, for example, switching power supplies. So this is what you have to take. You have to be aware of when you are analyzing these results. And of course, we haven't seen any spikes yet. This is expected because we did not add any stimulus. This we can do in the next minutes, where you can include one of the lines that say create a stimulus. And we do not only have to create a stimulus, we also need to connect the stimulus. So if you, the creation of a stimulus is similar to the creation of a neuron, but this stimulus does not have a physical counterpart on the chip. These spikes from external stimulus will be sent in via the FPGA. So let's run this example. Basically, you can uncomment anything that is there. Yeah? Here I did only the minimal parts. I create the stimulus, and then I connect the stimulus. And that's all you need to do. Yeah, and what we've seen here is that the blue line is the membrane voltage of the first neuron, and it's spiked 3 times. And this is what you also see in the spike raster plot below. And here you can see this noise that is visible here, and you can also see that it's correlated because also the other neuron picked up the same noise. This is some 2 readout lines that are close to each other, so they are very likely to pick up the same noise. Yeah, and basically now it's up to you what you do with this. You have now everything at hand to run an accelerated analog neural network, and this is where, so to say, the modeling part starts. Yeah, so now you can, for example, try to make the second neuron spike when the first neuron spikes, or you can start to inhibit the other neuron. So you can play around with this. So what you could also do when you want to have some kind of functional network, you could try to make a small chain of activity. But I let you first play around with only the minimal parts, so 2 neurons and a stimulus, and let you explore the options you have. So if you play around in the next 10 minutes, then you get a feeling for it, and then we can start to to make a minimal version of a, let's say, functional network. And if you have any questions, then we are glad to assist.
So I think stimulation already worked for all the
Mm-hmm.
and he had some old workspace somehow. I don't know.
Okay, good.
Not happened, but
No. The hash of the user ID was not. Yeah. Okay, so although this is already quite graspable that you have populations of neurons and projections between them, sometimes you want to know what at the end is really configured on the hardware. And for this, we have a visualization that you can access by first downloading the file that is generated below, store it somewhere on your local machine, and then upload it to our visualization, which is the link at the very end. So this should open a web page where you first need to choose a file that you want to upload. And then you click on the upload button, and you should get a view of the wafer and the connections that were drawn. Das gleiche Problem wie Tobias. Ich habe auch den Browser neu gestartet, aber das taucht nicht mehr auf bei mir. Der Upload geht nicht mehr.
the file just came there. So this instruction just generates a link. The file is generated by our software stack. So if you look at the coding, there's less. It says persistent. It's our persistency file. So it just stores the viewer is should not behind that link. Yeah, it takes a bit the loading. That's as long as it loads. But it uses some JavaScript libraries, they are not so
Is each one of the numbered blocks in the visualizer, is that one of the folders with 512 rows?
Yes.
Yeah, okay. So that just means my model is running on this board right here.
You
Yeah.
can zoom in a bit.
Oh,
Right.
well.
Slowly.
There we go.
Okay.
Cool.
Yeah, right. And how the menu disappeared. It's there we go. And you can click on these checkboxes. And you see the routes that the software choose to transport the signal.
Oh, okay.
So on here is the the spikes go on through this way. So they're injected here where the red arrow is on this chip, and then you have some chip. For example, go to the IPython notebook again, and go up a bit, and then let's place the stimulus to some other chip. For example, if you just implement this environment again, the full machinery,
Okay.
you can see some more chips that are traversed. Because it tries, of course, to inject as close as possible automatically.
Oh, and
and
you're
now we start
okay. Okay.
pulling it apart to see more of the infrastructure.
Okay, cool. Thank you.
Sorry, I pressed the wrong button. I think there's something cached in your browser.
Ja, das habe ich auch
Because-
gedacht, ja.
Do you have another browser?
Habe ich auch schon probiert, war das gleiche. Chrome auch.
Strange.
Mhm.
It works for me and the others.
Ich weiß.
Yeah, but
It's not working for me.
Not working for you.
which browser? Edge.
Yeah.
I was just wondering where the visualization tool came from. Did you guys make that yourselves?
Yes. This was a bachelor thesis of one of our students.
No, it should work in Chrome. We tested Firefox in Chrome. It shows something. Maybe toggle the images one time. It's not. Can I just do reload? Maybe. That's right. Yeah. So this XML file is really just a serialized data structure for the wafer configuration. So you have for each chip in the system, you have a hierarchical data structure that contains all the neuron configuration bits, analog parameters. They are all stored in this XML file.
My trouble now the two stimuli, one is located on the chip where your neurons
Yeah.
are, and the other we put there.
yeah,
On the routes, I see that it traverses these chips.
Yeah, it's not perfect, the visualization. It's really. Sebastian, should I attach my laptop? It works at my laptop.
Yes.
Maybe. Just for the. to show it.
HDMI groß.
HDMI. Maybe just. Should I use it? Should I say something?
Mhm.
Okay, so not yet the same. Yes. Okay. Okay. So that's what you should see approximately. So you can, if I zoom a bit out, you see. Okay. Now you see a coordinate system. So that's the complete view of the wafer. So you can see here the wafer, the individual reticles, the building blocks of the wafer. You can see in different coordinate systems. For example, that's the FPGA numbering. So FPGA 12 is here, and FPGA 0 is here. So it's a bit strange, and that's a different numbering scheme. If we zoom in a bit, we just get a view of all the HiCan chips, of all the individual building blocks that contain 512 neurons each, and one of them is a bit highlighted, and that's the one that I'm using currently. So for you, it's a different one. That was this boilerplate part in the Jupyter Notebook script. And if we zoom in here, we can click it. You get a number which says 2 neurons are used on this HiCan number 8. And yes, we can now. Yeah, we cannot see much more because we did not use any synapses yet, because I just run the experiment in the first version. So I will just maybe activate the stimulus and attach it to both neurons and run it. Okay. Okay. Download link and upload again.
So as you can see, this is work in progress. The visualization, you explained it, is really, we did it our own. What we do is we use our C++ code, which is the main software stack, and we transpile it into WebAssembly and add some JavaScript on top for the visualization. And yeah, some parts, the parts that do the deserialization of the data structures are not yet really optimal, so it takes a long time even for small networks, but it does not, it's really an overhead. So if you load a large network, it gets slower, but not super slow. So you can view almost wafer scale experiments. So what you can see now is you see some kind of a orange vertical strip here and a horizontal one. That's just a statistical view of how many horizontal and vertical lines are used on this chip of this on-wafer bus structure. What we can also do now, and you can also see the red triangle in the bottom. This means we have some input here. It's also shown in the second in this second color-coded strip. We can now activate the visualization of routes, and now we get this blue, light blue line shown, a vertical one and the horizontal one. We can also zoom in and see some switches set. So this is the white dot is really a bit that you can set in the hardware configuration to connect the vertical and the horizontal line. So that level of configurability is really represented here in the visualization tool. Okay. And what you can also see is that the horizontal lines, they really go from one chip edge to the other chip edge. And then you can, for example, if you use multiple Huygens for an experiment, you can choose to prolong this connection and really repeat it and have the same signal on the next chip. So you can really build large routes. So it's a circuit switched model of communication. So it's a bit like a very old very old telephone system where you really created channels between two partners, and that's what is done here by the software. Did you want something else to be explained?
No, also works by me.
Switch back?
Yeah.
Okay. So we'll switch back.
Okay, so in the meantime, I set up a small experiment where I had a chain of neurons connected in a ring-like structure, and at the start I excite the first one, and then the excitation propagates, and then it wraps around to the first one again, and continues until I send a strong inhibitory stimulus to all neurons, which then ends this information that goes into in a circle. And you see that this is very controlled propagation of this excitation, and this is achieved by having a backward inhibition. So I do two simple things. I have two indices that go over the population of neurons I set up, and then the first one to the next one excites, and the next one to the previous one inhibits, and here I just close the ring. So you could think of this as
the inhibition of the last step is missing, right?
The inhibition of the last step is missing. Yes, it's off by one problem, but doesn't matter. So you could think of this as you have stored one bit of information. You can activate that chain, and then it will run forever until you deactivate it again. And of course, you could use this chain then to control something else. So this could be a simple building block of a larger functional network. So we can see what happens if we remove this backward inhibition. So then I expect that the network gets somehow epileptic and does not propagate this information so in such a controlled way anymore. So if you build these networks, you always have to think of how the device variability affects your result and how you can compensate for that. And there's a whole set of ideas how to compensate, for example, for too weak synapses or lost synapses. Yeah, and in the meantime, our result got back, and you see that here, after a while, one spike makes the next neuron spike twice, and then somehow avalanches, and then in the meantime, or in this middle part of this chain running, you basically have everything active, which is maybe what you want. Yeah, you get more activity by this. You can also deactivate it, but it's not a controlled propagation of this excitation. So if for one reason you don't like this inhibition, you could play a different trick. You could, for example, play with the neuron parameters and make the refractory period large, which is the time after which, when a neuron spiked, cannot spike again. So this would, for example, help to remove this double spikes. And we can also try that and see if this gives us another way to compensate this avalanche behavior. Yeah, and you see it looks quite similar. You see this large refractory period here, but you are again at the point where you have this controlled propagation of excitation. So there are always different means to make your functional network behave in the way you want, and this is a game of playing with resources. Yeah? So all inhibitory synapses, for example, could be just too much for a large network. So in this case, you would rather use the refractory period method. But this totally depends at the end on the application. It's not known a priori which is the best way to go. Yeah, so this is the view of this network, and you see that you have some more synapses here. But this, as you see, is still far away from the number of synapses that this single chip has, let alone the synapses you get when you would use the full wafer. Yeah, so get an idea of what hopefully we are going to show soon, that these large networks can really profit from the acceleration factor, so that you really have a large fabric where you can conduct your neuromorphic experiments on.
I have a question. So I'm a computer scientist,
Mm-hmm.
and I'm kind of curious. Can you build? Is there like a strategy to build large circuits? You know, like if you're writing a program,
Mm-hmm.
You'd start with like your functions or your objects.
Yeah.
And you test those functions and objects, then glue them together.
Mm-hmm.
Can we approach this paradigm? And is there an
Yeah.
analog to?
Yes. So there is this neural engineering framework from Chris Eliasmith et al.
Okay.
They translate basically linear algebra to a rate coding way of handling it. So this is really an engineering approach. This is not necessarily anywhere close to what a biological network is doing. Yeah. But yes, you can.
Okay.
Yeah. If
And
it is
on
beneficial.
the other hand,
yeah.
and there are also, I mean, we have for our experiments, we have an approach of doing, for example, unit tests of individual parts. But the individual parts are still somehow designed in that way. So, for example, we have a part which generates, let's say, background noise. So on the wafer, just to not have to provide external stimulus just for background noise, for Poisson's stimulus. We have maybe networks that do this creation of the background noise on the wafer. They are
blocks.
tests.
Yeah.
They are building blocks in that sense,
Yeah.
but they are not building blocks in a mathematical sense. So they are just, they fulfill some function,
Mhm.
but you still have to know, you have to connect it in the right way to the rest of your network.
Okay.
Or for example, in another experiment that we did, not on the BrainScaleS 1 system, but on the BrainScaleS 2 system, we have an unsupervised learning mechanism that requires certain aspects. For example, you need a certain neuronal activation function, so it should react in a certain way. You need homeostasis to control your output firing rates of the neurons that are involved. And these are all building blocks for the full experiment, so you have to check each of them individually. They can be tested in continuous integration systems, for example, and we do it.
Okay.
But it's not like a programming language. It's really still a graph description of a neural network, individual parts, and you test each one individually. You put it together, you test it again. Yeah.
But apart from that, there is no agreed upon way how networks should look like. Now this is
Right.
this is under research. Yeah,
Yeah.
you have some ideas from neuroscience, from animal experiments, how these networks could look like, and there are more and more recordings of alive neural networks that fulfill a task. But this is really difficult because in an animal you have so many neurons, so many connections you cannot monitor. So this reverse engineering of functional networks, this does not exist yet. Yeah. So this is up to research, and this is why we think it's so important to have a substrate that allows to explore different approaches to functional networks in an efficient and fast way. Okay, so if you have played enough with the first generation system, I'd like to suggest that we start with the introduction to the second generation system, and then you can run some examples on that platform as well. Thank you.
Okay. Then we switch now. Laptop. Okay, so let's switch to the second generation. So if you go back to the Jupyter Notebook Explorer or file viewer, you can see the BrainScaleS 2 tutorial folder, or if you don't see it, just click on this symbol here to go to the main directory, and there should be the BrainScaleS 2 tutorial folder. In this folder there's again a Jupyter Notebook file that you can open. And first of all, the Jupyter Notebook, no, it's there. Okay, was not mainly created by me, but by two other people. I mentioned them here. That's Philipp Spielger and Timo Wunderlich, those two guys from our group. And yes, they put quite some effort into making this really a tutorial for people that don't know the system yet. So it's currently the BrainScaleS 2 platform is more of an hardware research platform. We just taped out the first non-prototype chip, so the first full-size chip, 4x8 millimeters, I think, with 512 neurons. But this is not used in this tutorial yet. This tutorial still uses the old version 2 prototype, which only contains 32 neurons and 1024 synapses. Compared to the BrainScaleS 1 system, it's also a bit slower. It's only 1,000 times faster than biology, instead of the 10K speed up of the BrainScaleS 1 system. Yes, we did this because of careful consideration of the bandwidth limitations that we have in the BrainScaleS 1 system. It really looks more like a better sweet spot with respect to the environment, computer-wise and host environment-wise, compared to the 10K speed up. Just all the bandwidth limitations just are tenfold relaxed, so you have a bit more headroom. Okay, so if we now compare the feature set of the two chips, or the chip generations, one major thing is different between BrainScaleS 1 and 2, and that's the embedded processor. So on this system here, we also actually have a setup here. So if you did not look or did not visit our demo setup at the poster session, we used this setup at the demo session to execute some experiments. The chip that you can see on the slide here is below this dust cap. So it's not that interesting. Basically everything that you can see on this board, on this printed circuit board, is power supplies and I/O interfacing. So some USB interface to connect to a host, some cooling of the FPGA, which is below there, and the chip is really just on this rather simple daughter PCB. Okay, but the processor is embedded on this chip, so it's really a small processor sitting directly next to the analog neurons and the synapse arrays. And this is a nice feature because using this plasticity processor, that's what we call it, PPU, you have fast and low latency access to quite some observables in the system. So for example, you can access correlation information which is acquired and also stored in the synapses. So each of the synapses in the system, so each synapse in the synapse array measures individually pre-post and post-pre pairings of the spike trains. So the spikes that go into the synapse and that the postsynaptic neuron generates. And they are weighted according to the STDP curve. That's basically what you maybe know from the B and Poo publication. Well, yeah, it looks a bit different, but the biological measurements are always a bit more dirty. But that's basically these two exponential functions. And you use basically these delta t's on the x-axis. You acquire some value y on the y-axis, and this is accumulated onto a local capacitor in the synapse. So you have an accumulated correlation information available per synapse. And this is quite cool because you don't have to compute anything to get this information. It's really happening massively in parallel. So your plasticity, if it only requires accumulated spike train information, correlation information, you can really use this massive parallel scaling of the synapse array and do the processing of this correlation information in the programmable processor. So you just read out the accumulated correlation after some runtime of the experiment. You evaluate it. For example, you want to apply a weight update according to the STDP curve. And you just do the weight update and let the system accumulate more correlation for the next update step. So you decouple the measurement, the low latency measurement, from the update, which can happen usually in another slower time domain. So that's one main functionality. Other functionalities are like neuron spike counts. You can look at the spike rates in the neurons. This can be used, for example, for homeostasis functionality, so you can control your firing rates. In principle, you can also look at the spikes themselves, but this also means that the processor has to handle quite some data if the spike rates are high. And that's usually not what you want in an accelerated system, because the spike rates are really quite high due to the acceleration factor. Okay, controllables. You can set weights from the processor. You can change connectivity. You can basically change any digital configuration bit on the chip. You can change the analog parameters of the neuron during network operation from the processor. So it's basically the same as the host computer, but with an additional feature that is really real-time controlled what happens. Okay, so what we can do with this is STDP, all kinds of STDP, reward-based STDP, structural plasticity, homeostatic rules, other things, yeah. We also have now a publication which combines basically quite a few of these features into one experiment, and it's called Demonstrating Advantages of Neuromorphic Computation, a pilot study. And in this publication, maybe I find the picture. Oh, was it here? Yeah, here it is. We use the processor, the embedded processor, for two things. We use it for plasticity and for virtual environment simulation. So we simulate the Pong game, really simple Pong game, just elastic collisions and a pedal that can be moved. And we provide the current ball position to the neurons. So we encode the ball position as spikes, send it to the neurons. The neurons react. There's a STTP involved regarding the weight changes, and we use the output of the neurons to encode the target position of the pedal. And over time, using an appropriate update rule, which is all described in the paper, here and here, for example, we can achieve a certain, quite perfect playing behavior. It's a simple task. It's a demo experiment, but it's, I think, the first experiment that really shows an accelerated system that you can combine a game, plasticity rules in a programmable way, and an analog neuron model and mixed signal system like the BrainScaleS 2 system. In principle, we can also interface this to the outside world, so not only virtual environments, but this usually means that we need some kind of accelerated robotics. Yeah, you have a question?
Mm-hmm. So I'm curious about the PPU. How complex, how much capacity does it have? How complex of environment could you simulate?
The current version that we run here is I mean, memory-wise, it's a 16 kilobytes SRAM only, so quite small. You don't have a full C++ standard library available. You only have.
What processor is it?
It implements the power instruction set architecture 2.04, and
I can say a few words. I've told this in my talk on Monday. This is the first prototype, and the idea is to go on this route. Next step, we'll have the memory interface so that you can implement any software you want, because you have unlimited external memory if you want to. And in the long term, we want to switch to RISC-V so that we have a standard processor.
On each core? On each
instead of the power
I see, yeah.
built ourselves.
Yeah. That'd be great. I'm really excited about the ability to simulate environments on the CPU.
Yeah, it scales then. Well,
What's that?
it scales then to any size, as many chips as you have.
Yeah, that's really exciting.
But regarding the processor architecture for the scalar part, so if you just do like what you usually do for the control path of your code, that's C or C++. So this does not really depend on the architecture. If it's now PowerPC on the prototype or later RISC-V architecture, this will basically feel the same. The difference, what's special here in this processor is the vector unit that we added, because we use this vector extension to access the synapses and certain other things on the chip. So for example, if you read out the correlation, you don't do it in a synapse by synapse way, but you read out a full line, for example, or half a line. So you load a vector register with a lot of values that you acquire from the synapse array. So it's a vectorized access for many properties. And also the weight update, if you just want to multiply the weights by a factor of whatever, you just do it vector-wise. So it's really a vector instruction. It's not, you don't have to step over all synapses, you just step row-wise, I think, So it's a vector processor.
So my second question is going to be more vague because it's not an area that I understand very well. But I guess, okay, so my first question is, with the neural network, is this really, can you think of this as a general purpose analog computer? Can you solve
No,
ODEs?
No. I mean, the neural model is really fixed. So the neural model, the differential equation that we implement in hardware, it's really, in this case, it's leaky integrated fire. So it's just
communication, it's spikes. It's not an analog computer.
Understood.
Probably you can, there are proofs that with enough neurons you can approximate any function.
Okay.
But I think this is not
Understood.
resource efficient.
I mean, what we also plan to do, but this is again not available in this prototype, but we have it in the latest chip that we taped out, that neurons can run in some kind of analog multiply accumulate way. So you can use it for deep learning as an analog computer in that sense, but it's really just supporting the multiply and the accumulate.
Okay.
Yes. Okay, so now we come to the contents, the real contents of this tutorial. So what we really do here is much more low level than the first part of the tutorial. In the first part, we really looked at neurons from a biological perspective. So you created, using the Pine API, you created some neurons, set the parameters in the biological time domain, for example, and you connected external stimulus, and the system was just doing everything to configure the hardware. In this tutorial here, we really explicitly configure the system, so you can see how internally things are done, and what the higher level software stack is hiding from you is I think will be clear at the end. So as a first step, we will again do what we did in the first BrainScaleS 1 tutorial. We will stimulate a single neuron, and for this we need input stimulus. For example, we chose for this tutorial here, we chose a Poisson spike train. So a Poisson spike train uses an exponentially distributed interspike intervals. So we have this exponential distribution where we draw some numbers. They are these interspike intervals are then accumulated. We get spikes out of this, and at the end we have to sort them because they are not in time sorted order, and I will explain why we have to do that. Okay, and the first thing is we can just define this function. So I just executed the first cell that can be executed. Then we generate some spike trains here, and we can plot it. Now you can see something like that. There's a random number generator involved, so it always looks a bit different. So that's just a Poisson spike train. Okay, so now we come to the hardware configuration. The first thing that we have is here some boilerplate code. Again, just to select a hardware system. In the morning session, we had quite a few users, so like 20 or something. No more. It was more, but so we really needed different chips. So now it's maybe a bit more relaxed, but in this case, we just use the username and select one hardware system based on the user ID. Okay, so the first experiment. I should maybe increase the size here. Okay, and full screen. Okay. If you're familiar with Python, I think you understand most of the lines here. So we import some functionality from Python libraries that we created. So for example, the dlens library contains all the C++ Python wrappers that we created for the low-level configuration of the system. We have, for example, a coordinate system. So all parameters or all indices which are used to identify individual parts of the system. For example, the 7th neuron on the chip, they use a C++ type, and this is basically directly wrapped to C++. So there's a coordinate system. So for example, neuron on DLS is now a type which gets compiled. In the C++ case, it gets compiled to an integer, but from a C++ view, it's really a type that has a parameter range and also checks the parameter range, and it checks it for constant parameters. It also checks it during compilation. So you get, for example, compile errors if you want to use synapse coordinates to access a neuron. So that's just to reduce the number of problems that you can create when using the wrong indices. We use basically typing for everything. The main functionality of the hardware configuration is now hidden in this tutorial configuration file. I will just open it quickly and browse over it to give you an impression what has to be done on this abstraction layer level of abstraction in this layer. Okay, so for example here there's a class which is called tutorial board. So this is the board configuration. What we mean by board configuration is basically everything which is off the chip. So on this board there are many configurable units. So for example, you can configure reference voltages, reference currents, I/O parameters, stuff like that. That's hidden basically in the board configuration. And one example here would be a bias current for the capacitive memory, which is our on-chip analog parameter storage. So we store analog parameters in something which is called capacitive memory. And this memory somehow needs some reference currents. I'm not the expert for this. There's a hardware guy in the back. But yes, stuff like that has to be set. Okay, then there's a chip class, which derives from a container. We call it container class, which contains all the controllable settings of the chip. So digital settings like neuron bits in the neuron configuration, which enable, for example, a neuron or disable it, the spike output, for example. And that's in this chip class inside. And here we do some basic parameter settings to get functional neurons and some base calibration so that neurons are working in a certain range and you get reasonable output. So for example, what you also have to do, I have to say basically all parameters are usually set to false as a standard, so you get basically a silent chip when it comes up. Yeah, you have a question?
Yeah, whenever.
Okay, so the chip comes up silent and does basically nothing. You have to enable everything to get basically function. And we do that because during commissioning it's really not fun if you have a chip that produces output all the time and you don't know what's happening. So we default everything to off. And therefore you have to set a lot of parameters to an enabled state to get function. We also have to set neuron parameters, for example, threshold voltage for the neurons. That was also done in the first part of the tutorial, but there we used biological units like minus 17 millivolts. Here we use digital values. 460 is a digital value that we use for 12-bit DAC, so it gets converted to a voltage internally on the chip. There are lots of bias currents for different parts, different circuit parts. That here, the E reset, for example, is a reset potential of the chip. This is now global on this chip. On the larger chips, it's global per hemisphere, so you have two chip halves, and the upper half has one configurable reset, the lower part has one. If you would require from a higher software level, for example, the Pine layer that we have shown earlier, if you would require, for example, two different reset potentials for two neurons, you would place them onto different parts of the chip to achieve this. So not all parameters are individual per neuron, but some are shared for multiple neurons. As I mentioned before, neurons have to be activated, the digital output, otherwise they won't spike. Or they will spike, but nothing will happen on the outside because the axon is basically off. We have to enable the synapse input circuit, so for excitation and also for inhibition. Otherwise, you won't see any change in the membrane potential. We also have to enable the leak to basically the resistance to the leakage potential. Otherwise, it's basically infinite. Yes, some other parameters. Yes, I don't have to show everything. It's really just to get the chip running, pulse length, whatever. Okay, good. Back to tutorial. This is now hidden in these two tutorial chip and tutorial board classes. What we add now here is just an execute function that takes some parameters. I will explain them when we use the function. And what we do in this function is we configure, again, the leakage potential. That's a user-defined parameter that we get in this execute function. It's the first parameter here. So we set all neurons to a leakage potential that the user defines. Now, in this part, can you see the marking? Is it visible?
Mm-hmm.
Okay, so we create a synapse configuration. So the synapses can be also configured. And they not only have a weight, which is one part of the synapse configuration, but they also have something which is called address or filter label. And what the synapses can do, they can basically listen to a set of input stimuli, labels that arrive over time. I mean, based on the timestamp of the individual spikes. And they can compare their internally configured address to the address that gets sent in. And if they match, they get triggered. If they don't match, basically the synapse is not used for that connection. And this can be, for example, also used for structural plasticity, because you can reconfigure the synapse during runtime to listen to a different signal that gets sent in. And over time, you can, for example, do this based on the current weight of the synapse. So, for example, if your STDP rule creates a large weight for a certain synapse, you keep it with a high probability, but if the weights are decreased over time, you replace it by a differently configured synapse with a higher probability. For example, it can be used for this. Okay, so now we have a configured synapse. And then this is basically the main part of the experiment runtime. So we have something which is called Playback Program Builder. That's basically a class which allows you to create an experiment protocol. So you have basically events that you want to execute at certain experiment timestamps. So for example, you want to inject a spike at a certain time, or you want to read out a synapse weight at another time. So you have events, and you want to execute them at certain points in time. So one example would be spike train. So we generate a spike train here, and now we use this. I could also, maybe I should have moved this down below here. Now it's a bit more logical. Okay, and here we create this playback program, we call it. That's basically the set of instructions that the FPGA executes during network operation. So it, for example, can send down these read commands or write commands, or it could also send down spike events, and they can be sent down to the chip. Okay, the first thing that we usually do is we set the playback program time to 0, just to have a defined starting point. So there's a counter in the FPGA that just counts upwards always, and you can reset it to a certain time. And here we iterate over all spikes. We add a wait until. Wait until means wait until this time is reached. So we provide a target time, and we wait for it. And at this target time, we inject a fire event into this program, which addresses a certain synapse driver. That's basically a row in the synapse array with a certain source address, and that's basically the part of the information in a spike that has to match the synapse configuration, so that the synapse really releases or gets triggered. Yeah, if the addresses don't match, the synapse just does nothing, and we do it for all the spikes in the spike train. So we have basically that's the representation of the input spike train in the FPGA afterwards. The last command that we add to the playback program is a halt command. We use it just to check if the experiment has been completed successfully. If this halt command is not reached, we can read out basically a status register from the FPGA, and the FPGA will flag some errors. For example, if the experiment is not successfully terminated using the halt command, there will be another flag, active flag, which mentions this. Okay, that's now, we call it builder because it uses this builder programming pattern. So it's basically this instruction here finishes the program and produces a data structure which resembles the runtime part of the experiment. This information, together with the static initial configuration of the board and the chip, can be then used to run an experiment that's provided by this, or possible using this run experiment function. Afterwards, we read back the spikes that have been recorded by the FPGA and return the input spikes as well as the output spikes, and this can then be used in our experiment here to create a nice plot of the input and output spike trains. Here we call this execute function. We provide a certain leakage potential value in digital units. It's not biological at all, so some digital units. It's not even a voltage in the hardware domain. It's just really a DAC value for the digital to analog converter. Okay, we provide a target interspike interval of 200, and 200 means 200 clock cycles, and the clock cycle on this chip in this configuration is 10.2 nanoseconds. So this means every 2 microseconds, we want to have a spike on average. It's a Poisson process, so yeah, it will be stochastic. Okay, that's just the neuron that we want to use, and that's the experiment runtime. Okay, I've written the script. Here we can execute it. It basically works like in the wafer case. It looks a bit different. We select a different queuing partition. It's not the wafer partition, but it's the PLS prototype setup partition. And here you can see, if you know maybe Singularity, that's our container. It's a bit like Docker, but you can use it in HPC environments, so that's why it's nice for cluster usage. And here in the end, we have the Python stage 0.py command, and this runs the experiment. Okay, we can do some plotting. We see the input spike terrains, stochastic firing pattern, and some more regular output pattern of the neurons in this case. It might look different for you. Okay, so did you try to execute the cells? Did it work? Okay, good. Then that's basically what we did before. It's boring, more or less, because it's just a more tedious description of the same thing. Just some software layers are missing. But the next stage here, 0B, is more interesting, because here we use the embedded processor to execute some function or plasticity change, or sorry, weight change. It's not really plasticity in that case, but it's a weight change over time in the experiment during the runtime of the experiment. And if you're familiar with C or C++, I mean, if you know Python, it's also okay. So here we include some header files. That's standard C header files. We have some helper header files that just provide some functions to access, for example, synapse array, time register, neuron counter, neuron spike counters, stuff like that. That basically all these software parts are available on our GitHub. I did not yet open it. So there's github.com/electronicvisions. That's our group GitHub. We have like 71 repositories in there, and we can search for this libnux library repository, and here you can, for example, look into this folder libnux, and here you can see the header files. For example, a header file for the counter, read out version 2, and here's an implementation of the access to a certain neuron counter. So, for example, neuron 0. If you want to read back the spike count of neuron 0, you would provide a neuron 0 here. There's a base address where you have to read from. You add the neuron offset, some pointer conversions, reinterpret cast. Yes, and you get basically the output and you return it. So for many things it's easy. For some other things you have to do some bit mangling, just because it's not a word-wise access that you have. Yes, so there are a lot of helper files. And actually everything is there. So you can also look in our linker file how we link together the software. So for example, if you're interested how the program is structured, you can really look here. Okay, that's the text section of the binary. You see, for example, stuff for C++, the function that gets called if you call a pure virtual function, which usually just terminates your program. But on the embedded processor, there's no terminate function, so you have to specify what should happen if the user code does something illegal. Everything is available there. Okay, we go back to the tutorial. And in this case here, the interesting part starts here. So that's the entry point of the program. So it's like your main function if you write a C or C++ file on a Unix or Windows system or Mac. You usually use the main function. In this case, it's called start, just to make it a bit, to make it clearer that this is not a hosted C or C++ environment. It's really standalone. So you don't have standard library support, to a large part at least. Okay, what we do is we specify some variables. For example, here is a variable which is an unsigned integer 8-bit wide, but it's a vector unsigned int 8-bit. So it's really a vector register that gets allocated for the real operations, and in memory it's represented as a memory section that is aligned accordingly, so that you can really read this register, this memory location into the register or write it out to memory. So it's like you would do it for other data structures. Here it's just a vector data structure, and that's basically what we did, or what we provided in our modification of the GCC compiler. So we also have on GitHub a modification of the GCC, and this particular version of the GCC just supports additional vector instructions for the BrainScaleS 2 embedded processor. Okay. So there are some other variable definitions. That's now an interesting thing. So here we can read weights from the weight matrix. So we access the weight matrix and write the results into vector registers or vector variables, these two, left and right. That's now a technical thing. The width of the vector access is not as wide as the full row width. So you have to you have some striding going on. So you have a left vector and a right vector. So you have to provide two vectors to read in a complete row. And the real plasticity kernel, if you want to call it like this, is basically in this while loop. So we have basically a loop which checks the current time and compares it against the experiment runtime. And as long as the time is smaller, we execute some kind of code in here. And what we always do is we take the current weight value and we subtract 1. So this vecsplat U8 instruction fills a vector register with value 1 in each individual item. So the full vector is filled with ones. And we subtract it from the current weights. And then we write back the weights in the synapse array. So what happens is basically we decrease the weights over time. And as soon as we reach 0 in here, we subtract 1 from 0 and we get a flip to the maximum weight. So there it's in this case, the minus is not an saturating subtraction. So it's really wrap around and you get maximum weight again. And then we sleep for some defined period, 10,000 clock cycles. That's 100,000 nanoseconds. And we continue again. Okay, then we can try to compile it. So internally we have, all this is supported by our internal build tool. So usually you don't have to call the compiler yourself, but in this case I want to do it manually just to make it clear what happens. So a lot of options here. For example, we select the CPU architecture, we define the program to be freestanding. We do not include runtime type system things, so no dynamic casts for now. You can enable it if you want, but it has some memory overhead. And yes, and at the end there should be the CC file, yes. And we compile it, okay. In the next line here we link it. That's just as usual, just linking it with some other libraries, for example the libnux thing. Okay, linked. And as a final step, because there is no operating system running on the PPU that can interpret the output file format of the linker, we extract just the binary bits, and we will use this binary part of the executable to, and we will load it onto the PPU memory, to have the PPU executed. Okay, so. Now the program, again, it's very similar to before. If you look closely, basically the only difference that you will see is this. So what we do here is we use this binary file that we generated, and we load it, and we store it in a data structure which is called PPU memory. That's just the data structure that represents the PPU memory configuration. So all the memory words and control settings of the memory. Here we just pull the reset, so the PPU usually runs if you don't pull the reset. So we pull the reset, so it's a false because it is called inhibit reset. Then we write this command to the FPGA. So the FPGA executes this. Then we write all the PPU memory. So basically our file gets written into the static RAM on the chip. And we release the reset. So at this point here, the PPU will start running. And afterwards, the FPGA, that's still the program building here. So we will inject the spikes afterwards. So first, static configuration of the board and the chip. Then PPU configuration. And directly afterwards, we will start to send in some spikes. And again, running the experiment. And that's the caller part. We can execute it. And we can plot it. And what you can see here is first of all, you see a large input spike train over here. So it basically looks like a continuously firing input pattern, but it's still a Poisson spike train. It's just we zoomed out. The experiment is so long that the input spike train looks like a filled bar. And in the lower, the lower spike train, this now shows the output spike train. So we have some firing going on, and over time the firing rate decreases, and at some time, so for example here, we do not get any firing anymore, so that the weight is basically is getting too low. And at this point, it switches from 0 weight to maximum weight, and we get again some firing over time. And here it switches again, firing again, no firing, and it switches again. What we can do, for example, now, I can open this C file, the spike counter loop decrease, whatever, over time. And we can change some parameter. For example, the sleep time. So the basically the wavelength of this firing pattern here. So for example, we can decrease it by a factor of 2 and save the file. We have to recompile, so we have to get to the compile commands. Compile, link, extract the binary data. The host file can stay the same. We run it. Okay, and we can plot it. And you see the frequency of this modulation of spike output, spike rate output modulation. It doubled, because your program basically waited only half of the time now. Okay, so that's basically the simplest program that you can, at least functional program that changes something that you can have. Now we can, for example, also look at multiple neurons in parallel. So for example, we can look at this neuron activation curve. So what we usually do, for example, sometimes you want to just record the correlation, the relation between input and output. So so what you usually get if you just have a silent neuron and you increase, for example, you increase the leakage potential over in a sweep, you will get basically 0 output spikes up to a certain threshold, the threshold potential, and then you get basically an increasing spike rate up to the maximum firing rate, which is defined by the refractory period, at least in the leaky integrated fire model. What we want to do here, we want to basically have a smooth transition from no activation to a certain activation, and we do this by by making the membrane stochastic, and we do this by injecting excitatory and inhibitory noise onto the membrane of the target neurons. And this is now done in this new execute function that we have in this second example here. So this all looks very similar. So you configure synapses, Now you have to configure 2 synapses because we now also have an inhibitory background synapse. We now have to generate 2 spike trains because we want to have uncorrelated noise on the excitation and also on the inhibition. We inject both spike trains, so they are now combined in this line. We inject both spike trains into the FPGA and we run the experiment. Okay, I save it. And what we now do is basically we do a loop over the leak potential of the neurons from a DUG value of 300 to a target DUG value of 700 in step size 10, so 40 experiments. And we will read back the spikes from the FPGA, so there will be quite some data transferred, so this takes a bit longer. And we run it. So now 40 different experiments are executed, and we every time configure the full chip, the board, the spike trains, and we read it back. So this will take some 20 seconds. Okay, already done. We can plot it. What? Oh, okay. You can see now, no, I did not restart my Jupyter session, so it has already changed. So what I did initially, oh sorry, I normalized the activity with respect to the last point that I measured. So basically the firing rate at the highest leakage potential. So usually you would think that for the highest leakage potential you get the maximum firing rate or it already saturated. But in this example you can see that, for example, some neurons fire with a slightly higher firing rate already here. And what we can do, we can just look at the absolute spike count. So it's not normalized anymore. So we can see we counted up to 700 spikes in this experiment individually for all the neurons in parallel. And what you can also see here is that the neurons are not perfectly calibrated to the parameter. So because each neuron is different in this case, and we configured just a low-level parameter. So you end up with basically some variation, which just comes from the fact that it's an analog. There are many analog circuits involved, and each of them is a bit different. And for example, this neuron here is even more off. So there's like a 15% offset between the majority of the neurons and this single one. And yeah, that's typical for analog neuromorphic hardware. So that's what you usually get. And yes, what we also can do, maybe I'm not sure what the time is. Do I have some time left? Yeah, okay. Maybe the question, did you try it out? Just run it? Okay, it worked? Okay, yeah. Nice, good. What we can also do, just to maybe make use of the processor, we can also use the internal processor to read out the spike trains, so we don't have to transfer that much data. So we use some code snippet, spike counter loop. I will open it shortly. Wrong. Here. Spike counter loop. It's again very simple program. The kernel is basically this. So you have you iterate over all neurons. So that's the number of neurons. DLS number columns is the number of neurons. And you call a helper function, which is defined in one of the libnox header files, to read out the numbers. That's basically an operation which has been implemented as a custom functionality in our hardware. You read back the count. It also gets resetted in parallel. So this readout instruction also resets the counter. So the counter starts again from 0. And you accumulate this onto an internal variable in this loop. At the end of the experiment, so after this time frame has been reached, so the current time is larger or equal to the target experiment time, we will execute this code. And this code now just uses a variable which is provided by the linker, which is called random access memory end. So that's basically the last address plus 1, so the first illegal address in memory space. And we subtract the number of neurons. So basically we subtract 32 and we cast it to a word address. And then we get basically the last portion of memory where we want to, where we can write into the spike counts. So we just use this magic memory region for communication with the host code. So that's basically just for writing the data onto a defined memory location. And if you look now into the host code, there is now not only this reset things going on as in the first PPU example, but also some read commands are added. So for example, let me check, where is it? Here. Here we add a read command which reads back the status register of the PPU. So the PPU itself has a status register which can, for example, can be used to check for exceptions. So for example, if you do a divide by 0, for example, you get an error flag in this error register. So you can check this. And what we functionally do is we read the end of the RAM, and this is basically done by these two lines. So we have one line which describes the memory region that we want to read. So we want to read from 4096, so that's now the count in words, and our words are 32 bits, so that's 16 kilobytes. And we subtract the memory, the number of neurons, and we read up until the very last word in the memory. And we now inject this read instruction into the playback program, and afterwards we halt the program. Okay, so that's the difference now. That's how you basically do or implement timed reads on the BrainScaleS 2 system. Okay, we write the file. We compile the CC file that we had before, and we run the experiment. It's again 40 experiments, so we have this loop here over the different leakage potentials, so it again takes a bit of time. Okay, and here we saw an error, so the PPU somehow did not finish in time. I'm not sure why it happened, but I have seen it. I've seen it before, so I just try it again, maybe some glitch. Okay. Okay. And we plot it. Wrong. Where is it? Okay, so here you can see the activation function now measured for all neurons using the on-chip spike counters of the individual neurons. If we look at the absolute spike count, it's a bit different, but that's because I also changed the experiment runtime in here. So it just averages over a larger amount of time. So that's also why the curves are a bit smoother than in the example before. And again, there's a neuron which is way off, and even more off than compared to before. Okay, so that was basically the first steps that I wanted to guide you through. In principle, we also have a homeostasis experiment that could be now done. So you combine the rate measurement in your PPU code and the weight update, and you can basically implement homeostasis because as soon as you can measure rates, you can compare it to a target rate, and then you can modify your weights in a way that it reaches a certain target rate after time. What I can also do, maybe that's even more interesting, I just show you how we do how it looks in a real experiment. So I will just open our continuous integration server because we have some hardware experiments that get run on a nightly basis. And there's one where we have really a nice separation into individual functions in the network. So we have one step which just implements, for example, the winner-take-all network, and we verify its function. And we have a step that does the homeostasis, and we verify this function if it loads. Does it load? I don't know what's going on. Okay, this is loading. This is not loading. Maybe I just reconnect. He switched to the different network. I wanted to go in this network again. Yes, and maybe what we also can tell, we did not yet tell details. So if you're interested in using the system, we wrote down the URL, HTTP, the bottom one, neuromorphic.eu, and there are some instructions. So if you're interested in using the system, getting test access is very simple. So basically you have to only provide, I think, Björn knows it. What is needed?
You get a UP account, then sign the form and send us a scan of the signed form that you're not using this for military purposes, and we get an account.
Yes, good. Okay, and if you need, for example, if you want to do larger experiments and you need more, for example, more experiment time or more help, that's also possible. But then we need a bit more of a description what you want to do. And yes, so unfortunately our continuous integration server does not react anymore. No, it works. Okay. Yes, stuff. Okay, so that's one DLS prototype version 2 example. And it failed. Nice. Okay, so 2 days ago there was a run which worked, at least partially. So for example, here is a file. I click it, that's the activation measurement that we did in the tutorial. That's also part of this experiment. Okay, where's my browser? I closed it, okay. Back. Can I go back? Yes. Okay, what else? Some technical things are also done. So for example, if you need, for example, a calibration of some, that's now the column ADC converter. That's the ADC which is on the chip that is used for measuring, for example, the correlation information inside the synapse array. And if you want to, for example, calibrate it to know that it's linear in a certain range, you can, for example, have a test which tests this, and you integrate it into your experiment flow, and so you can test it on a nightly basis. That's, for example, one technical thing that you usually want to test. What we also do is, for example, okay, that's not interesting. Is that interesting? So we can measure, for example, the functionality of these correlation circuits and just check if the distributions look right. We can. That's also not homeostasis is I think quite interesting, but not that one. Maybe that one. No. So different kinds of homeostatic processes are checked. So for example, here we have a target rate. That's the orange line here, horizontal line, and we have the measured rate. And what we do is we have a background noise, which is not 0. So 0 is here. That's 50 Hertz biological. And that's an excitatory background firing rate. And at a certain time in the experiment, we increase it by a factor of, I don't know, 4. And so we have much more excitation in the network. And what we now expect is an increase in the firing rate. That's also visible here. But the homeostatic processes, so basically the homeostatic code that you implemented on the processor, pull down the firing rate of the neuron again to the target firing rate. And what you can also see here is the evolution of the synapse weights. So for example, you see that we have 2 synapses, first of all, one inhibitory synapse and one excitatory synapse. The inhibitory is 0 at the beginning, and there is some evolution of the excitatory synapse, so the algorithm tries to keep the neuron firing rate stable, and at a certain time it detects the rise of the firing rate and it decreases the excitatory weight until 0, and then it switches on the inhibitory synapse, and you see an increase in the weight of the inhibitory synapse over time. And basically this time constant here is defined by your update algorithm. In this case, it's a super simple one, but you could implement different, it's a control problem, as usual. Okay, and then it stays there because the input is basically constant. And again, when we switch off this strong input and switch back to the old one, we restore basically the weight. It's even lower than the old one, so you can see it was like 50 here, and here it's a bit lower, so maybe 30. So the excitatory weight also restores to a higher, slightly higher value as before. So that's basically a simple experiment. And yes, this can be obviously, if you have a parallel measuring system, you can also work with the vector unit to control multiple neurons in parallel. So for example, if you want to have a homeostatic controlled neuron firing rate of all neurons, you can also implement this quite easily by just changing the instruction and using the vector instructions. So this is now shown for 4 different neurons here. That nice plot. Yes, it's hard to understand these plots. Yes, so here are some plots that check the winner-take-all part of the experiment. And what we also check is the evolution of the weights in the experiment. So there are some target weights that are calculated by the algorithm, and we see that the target rates over time are reached for individual neurons. Okay, so that's maybe some addition regarding the question that you asked, but I think it's not the answer that you wanted to have, but to get. But this is it's really the way that we usually work with this kind of system. So you really have individual functional parts, and you check them, and you put it together and try to get it into a functional state.
Yeah, that makes sense.
Okay, so I think we can end here.
Yeah.
Do you have questions?
My only question is, do you have performance counters on each of the nodes? Can you measure, for example, the power consumed per core?
Per core.
Okay.
I mean, on the prototype system, we did measurements for the full chip. So, for example, for this this publication here, where was it? That one. We also give some numbers, but this includes not only the digital part but also the analog part. But I think the digital, so the processor, dominates this consumption usually. But we don't have consumption, so individual measurements for the consumption. In principle, it's not a problem because the power supply is not shared between the digital part and the analog part. So you have basically different pins that you could measure, but it's just not available on these boards.
What about aggregate consumption?
Yeah, this was done.
Yeah.
Okay.
Yeah, but it's really a difficult task to get solid numbers.
Because it's always a setup problem. So what's your benchmark? So basically, what function do you want to fulfill? And I mean, as soon as you see these picojoules per synaptic event or synaptic operation numbers, you always, I mean, the first question is always, what setup? I mean, it always depends. Is it the maximum firing rate of your neuron? Did the network do anything, or is it just one layer, basically continuously firing neurons? No.
Include overhead.
Yeah,
Yeah.
stuff like that. Is it a wall socket measurement? Yeah.
So at the end, of course, you should measure plug.
Yeah.
Yeah,
That would be the most honest measurement.
yeah,
But sometimes overhead is just artificially large.
right,
Would spoil the,
Right.
the idea.
So, for example, our FPGA code. I mean, we are not. I mean, we use FPGAs a lot because we need it to get basically the system's interface. But we are not interested in I mean, not that much interested in optimizing the FPGA code basically to a state where it is perfect and does only that what is needed and is super efficient in terms of power consumption. So that's, for example, that's one part of the overhead that we, for some measurements, include, but I think it's not. Yeah, I mean, you always have to consider what should be measured. Yeah. So, for example, I think there will be very soon coming out a publication from the Ulrich Rückert group in Germany, Bielefeld. They did some comparisons between Nest, Spinnaker, BrainScaleS 1,
Spiky.
and the system before BrainScaleS 1, the Spiker system. Not yet the BrainScaleS 2 system. They are thinking about this, but it's not in this publication. And they did some. Yeah, they tried to really be fair, and what they did is basically wall socket measurements. And yeah, I mean, it's an upper bound for the consumption.
yeah, that makes sense.
Depending on the question, we also did the measurements. So in some papers there are measurements for individual circuit things,
You
but
cannot give one number.
it's not one number. Yeah.
You can give 10 numbers, they are all true, but not simultaneously. Yeah.
Right,
Always depends on the application.
right,
So I think that's also a general thing. I mean, we had it in the plenary discussions. Good benchmarks, functional benchmarks, and optimized implementations that really are able to. I mean, you need something really functional to be able to compare with, and you should be able to optimize it for your system. So you have something where you say, okay, it won't get much better on this system, and then you run the benchmark. You check that the numbers are okay. So, for example, your classification rate is fine, and that's basically one performance number. And energy consumption is the next one. But this set of benchmarks is really only it starts to get done, but it's not yet there. There's not really a large set of benchmarks that you can just run. Yeah. So, but it's needed, yes.
thank you, that's a good
Okay.
answer, I appreciate it. It was useful.
Okay.
Okay, then.
So
Thanks a
the
lot.
Thanks, guys.
demo website, if you want to just continue, maybe if you're if
Tonight in your hotel room.
yeah, if you're boring, just
What?
bored, yeah, then yes, just use it and send us an email if you're interested in using it for the longer term, yeah. So we at some point, I think next week we will switch off the demo site at some point, yeah.